So let's talk about quantum mechanics from scratch. Can we talk from a application point of view from the modern world and see how that instrument or device is being made from the quantum principle and how it reshapes the future?
Absolutely. Let's start with something that's deeply tied to quantum mechanics, the semiconductor transistor. At the heart of every modern device, from your smartphone to supercomputers, are transistors that rely on quantum tunneling and energy bands in semiconductors. Quantum mechanics describes how electrons occupy discrete energy levels in these materials, allowing us to control their flow with precision. Without quantum mechanics, we wouldn't have the digital revolution. And looking forward, quantum principles are shaping quantum computers, machines that could solve problems that classical computers can't. So, the future shaped by quantum mechanics includes everything from more powerful AI to potentially life saving drug discoveries.
So what what was that semiconductor transistor that you are talking about?
I'm talking about the tiny electronic switch at the heart of all modern devices. It's what lets us amplify signals or perform logic operations. Without quantum mechanics, we wouldn't be able to understand how electrons move through semiconductors, and we wouldn't have the integrated circuits that power everything from your laptop to the internet. In short, quantum mechanics made the modern world digital.
So you talk about electron moving through semiconductor. That is what the main idea here, and the actually when it moves, their movement cause uh, release of energy, and that is a great uh, thing to observe.
Exactly. The movement of electrons in a semiconductor is all about controlling how they flow and how energy is released or absorbed. When electrons move between energy bands or across junctions, we can produce signals, light, or even use that energy for logic gates. It's that precise controlled dance of electrons that makes everything from LEDs to processors possible. Observing and manipulating that flow is what makes modern technology so powerful.
So let's take for example LED. Actually, first of all, LED
An
has
LED.
semiconductor. Then what?
So in an LED, you have a special semiconductor where electrons can drop from a higher energy level to a lower one. When they do that, they release energy as light. The color depends on the energy gap. It's a direct application of quantum mechanics, designing materials so electrons emit light efficiently. And that's why LEDs are so energy efficient. They convert electricity straight into light.
Okay, what are you saying about this designing materials so electrons emit light efficiently? What do you mean by that part?
I mean that scientists engineer the semiconductor structure. By choosing the right materials, often mixing elements like gallium or indium, they set the exact energy gap between electron levels. When electrons fall across that gap, the energy released is light, its color tied to the gap size. So by designing the material's quantum properties, they tailor the light's color and efficiency, whether it's for a red LED, a blue one, or even white light.
Okay, for designing this semiconductor structure, we need right materials like mixing elements. Okay, uh, then they have the exact energy gap between the electron energy level. Okay, what do you mean by that exact energy gap between electrons level?
The energy gap is simply the difference in energy between two allowed states that electrons can occupy in the material. In semiconductors, we have a valence band, where electrons normally sit, and a conduction band, where electrons can move freely and conduct electricity. The gap between these bands determines how much energy you need to excite an electron up, or how much energy is released when it drops down. In LEDs, When electrons drop from the conduction band back to the valence band, the energy gap sets the color of the light. That's the exact gap we designed to control the wavelength of the emitted light.
What do you mean by controlling the wavelength of emitted light? For that complex system, the complex material that we design, there we need to see exact how electron will transition. But uh, uh, given the voltage, that voltage would spark the material to do so. But before the actual material that is made, we have to test these things, and that the emission and absorption thing that will work there.
Exactly. Before creating a final product, materials are tested to understand how electrons transition between energy levels. When you apply voltage, you're giving electrons energy, letting them jump up and then drop back down, emitting light. By tuning the material's composition, engineers fine-tune that energy gap, and thus the wavelength or color of light. The emission and absorption you mentioned are key. Testing ensures the material will emit the right color efficiently before scaling it up into actual LEDs.
Okay, which principle we use here from quantum physics directly? Uh, First, we have to design such a very good semiconductor material so that we have the scale of working there that would exactly match, and we will get the required transition and
The key principle at play is the concept of quantized energy levels, fundamentally from the Schrödinger equation. In a crystal lattice, quantum mechanics defines allowed energy bands and forbidden gaps. By designing the semiconductor, we set that gap so electrons transition and emit light at a specific wavelength. Essentially, we're applying quantum mechanics to engineer the band gap. Once we get the gap right, we know what photon light will be emitted, all determined by quantum theory from the start.
okay, what gap you're talking about here exactly?
I'm talking about the band gap, the energy difference between the valence band, where electrons are bound, and the conduction band, where they're free to move. In a semiconductor, this band gap is what determines how much energy is needed to excite an electron. When that electron drops back down, the energy released as light corresponds to the gap. So the band gap is crucial, as it's what sets the color and energy of the emitted light in devices like LEDs.
Okay, let's talk about an example from LED in today's world. Which material they use and what are the parameters they observe? How do they experimentally and theoretically work on those principles to make a industry-ready product?
A common modern LED material is gallium nitride. It's widely used for blue and white LEDs. They precisely measure the band gap of GaN, which determines the wavelength of emitted light. Experimentally, they fine-tune the material's purity, doping, and fabrication processes to achieve the desired efficiency and color. Theoretically, quantum models predict electron transitions and energy levels. By merging these, they adjust layer thicknesses, doping levels, and other parameters until the LED meets industry standards: bright, efficient, and reliable.
So electron transitions and energy level, okay, that is good. But what do you mean by determining the wavelength of emitted light? I think that is the most important point. When light is emitted, then we see spark, and that instant of energy, the voltage is continuously applied, and that process happen continuously. Then we see glowing in the LED.
Exactly. The wavelength of the emitted light is directly tied to the energy difference when an electron drops from a higher energy state to a lower one. Quantum mechanics tells us that this energy difference corresponds to a specific wavelength of light. By designing the material's band gap, we set that wavelength. For example, a larger energy gap gives a shorter wavelength, like blue, and a smaller gap gives a longer wavelength, like red. When voltage is applied, this process happens continuously, and that's how the LED steadily glows at a consistent color.
Okay, why when the voltage is applied, so given the continuous apply for the voltage, how that uh, for the semiconductor material that you mentioned about this gallium nitride, how it respond to this thing?
When you apply voltage to gallium nitride, you give electrons the energy to jump into the conduction band. Once they're there, they don't stay forever. They'll drop back down to the valence band. That drop releases a photon of light. Because GaN's band gap is stable, each electron drop releases a consistent amount of energy, giving you a consistent wavelength, say blue light. Continuously applied voltage keeps this cycle going, giving the steady glow you see in LEDs.
What do you mean by that consistent wavelength part?
By consistent wavelength, I mean that every time an electron drops from the conduction band to the valence band in that material, it emits a photon with the same energy. That energy is directly tied to the color or wavelength of the light. So if the band gap is fixed, the emitted light doesn't shift. This ensures that your LED always produces the same color, whether it's a pure blue, red, or white, every time it's turned on. Consistency is crucial for predictable, reliable lighting.
So when the wavelength is emitted from that semiconductor material, okay, so what is actually going through inside that complex compound, we can say that inside that their structure actually, can you comment on that part?
Inside that compound, it's all about atoms arranged in a crystal lattice. The elements, like gallium and nitrogen, form a periodic structure. Quantum mechanics governs how electrons can occupy specific energy bands. In the valence band, electrons are bound to atoms. When you apply energy, they jump up to the conduction band, where they can move freely. The crystal structure and atomic composition set the band gap. That's the core mechanism. Electrons moving between these bands emit photons, giving you that steady light.
So why only crystal structure you are talking about?
The crystal structure is key because it provides a repeating, orderly pattern that creates the energy bands. In a random arrangement, electrons would have all kinds of unpredictable states. But in a crystal, the periodic arrangement of atoms leads to well-defined energy bands and band gaps. This structure makes electron transitions predictable, which allows us to control the color of the emitted light. In short, that ordered structure is what makes the whole process work consistently.
So what is the exact idea to control the color of emitted light? What do you mean by that color part? Is that color uh, is uh, is a valid wavelength part?
Exactly. When I say color, I'm talking about the wavelength of the emitted light. Each color, red, green, blue, corresponds to a specific wavelength. When you control the band gap of the semiconductor, you're controlling the exact energy of the emitted photons. Since photon energy is directly tied to wavelength, that's how we precisely tune the color. So yes, the color is essentially just the wavelength of the light you see.
So let's talk about two things. What are the essential elements that we need to assemble theoretically and experimentally to make a ready product for this?
Theoretically, you need to understand the quantum structure, energy bands, band gaps, and allowed electron transitions. You calculate what composition and structure give the desired wavelength. Experimentally, you fabricate the semiconductor, growing it layer by layer. You test how well electrons move and how efficient the light emission is. Finally, you integrate it into a device, adding electrodes, encapsulation, and ensuring it's stable. In short, theory sets the design, experiments refine it, and then engineering turns it into a reliable product.
So, what are the things you like most about this discussion? Can you state that thing?
What I really enjoy is how it ties theory directly to something we use every day. We're taking abstract quantum ideas, energy levels, band gaps, and seeing them applied in technology like LEDs. Plus, it's fascinating how we engineer materials at the atomic scale to produce something as simple and beautiful as light. It's that blend of fundamental science and practical impact that I find really rewarding.
Thank you.